pretty similar distribution. Like how many of our number of outliers are there in heating gas, you see equal number of outliers in gas facility, right? Which means this heating gas is heavily influencing your gas facility. Overall gas consumption value is heavily influenced by the heating gas one. Okay. Now, these boxes basically tell you the 25th percentile to 75th percentile data. That's the distribution. So a lot of your data lies here. However, there are outliers as well, right? So this remaining, all the black dots that you see are each black dot is a single data point, right? So now there are 280,000 data points. In those 280,000, there are probably about 140,000 points in the box that you see here. And the remaining 140,000 are on the lower end or the upper end, like black dots, spread out, right? That's your box plot. Now on the bottom, when you look at interior and water heater, both of them are almost like lines. That basically means that most of your readings in those two columns are 0. And that's why they are still at 0. That's why the strong line. With maybe somewhere ratings are 1, 2, 3 or something like that. But it's because it's in a very tight range, you don't see much variation, right?
Okay.
So scroll up. Which one is the widest box?
The widest box is the electricity.
This one, right? Like the electricity.
Yeah.
Yes. So here, the consumption kind of varies all the way from probably somewhere around like 25, 30 or something, all the way up to maybe 100, 130 units, something like that, right? So that's the overall consumption value that you see. And that's the reason why this is the only column. And this is overall electricity consumption in the facility, right?
Yeah.
And that's why you see such a spread here, because there is variation in the value, hourly value.
Okay.
Right. And then which one has the least number of outliers?
The least, I would say this. The
Fans.
yeah.
See.
Oh no, maybe this one.
Interior lights, right? Yeah, that looks like there is. So there, and you can see the color, right? You can see the color and you can see the box. Although it's very slim, there is still a box. So there is some variability. Again, see, it's relative because you are plotting on an x-axis, which is going all the way from 0 to 4,000, right? Thanks to your outliers. And this is why outliers are bad. Sometimes you shouldn't consider them, right? So this is when you remove these outliers, right? These extreme values, your distributions will be a little more apparent. And you can do another aspect as well. Instead of doing this in all of these box plots in a single plot, do an individual box plot for each of the features.
For each?
Yeah. Okay. So you'll be able to.
Yeah. Okay. I thought I was going to be like end up being a lot of
visualizations.
EDAs.
That's fine.
So
that is fine.
Okay.
In fact, the more plots you have, the better your EDA is.
Oh, okay.
Okay. And one more thing. And the reason why I say that is, can you scroll back a little bit more? Scroll up. Yeah. You see these two things, the gas consumption and heating gas, their areas are super wide. And that's the reason why you end up plotting from 0 to 4,000. But if you individually plot interior lights, let's assume, right? The range that it takes is 0 to what? Probably 500, right? So given that's the only range, this box will appear a little more wider. Right? Because we are plotting all of these features in the same plot. Exactly. Together, it's turning out like this. But what you really want to do is plot them separately so that you actually see the spread.
Okay.
Okay. But good job.
So yeah, thank you. So we'll get rid of this because then I thought, okay, let's do box plots for like all the electricity, excluding the total, and then for the gas. But I think we'll take this out and then do the individual plots because the boxes
you could do for the total electricity as well. You could do one plot for total, then do the individuals, and then one plot for gas, and then the individuals.
Okay.
Right? So you could do that as well. Not a problem. You'll have probably like 7, 8, 10 plots. That's fine. The more, the better.
Okay. So this is the attempt to like do a violin plot and a swamp plot that I don't know, it took forever to run and then came up with this. It looks like, I don't know, I probably have to look at this some more and see what's going on.
So why
But
did the violin plot fail? But anyways, but that's good.
I
The
thought we had to
correlation
do
plot?
that.
Sorry?
Wait, what do you want me to show you?
Correlation plot?
Oh yeah, and then did this.
Okay, this is good.
I thought we had to do a violin plot. Maybe if we don't have to do it, I'll just take it out.
Could probably do that, not a problem. Wait 1 second. So heat and electricity is extremely negatively correlated. Kind of makes sense. Heat, but heat and every other variable is negatively correlated. Wait, hold on.
Now scrolling up.
Sorry?
Now scrolling up so you can see.
So heat and gas. Something wrong with this plot.
Yeah, I looked at it and I'm like, doesn't look right.
Yeah, because so we just saw that electricity, heating, gas and
I don't know if it's the colors that's like.
Okay.
So I think it's reading this
heat,
and
electricity,
this.
and gas.
Like
no, I mean it's matching each other by itself.
Yeah,
no,
it
I think
is.
I think it's fine. It's fine. I think this
Yeah,
it's just the way, for whatever reason, I don't know. It just looks. It's the colors that's like making it look the way it looks.
No. I was not bothered about the colors because I already saw the scale on the right side. Usually white's in the center, red's on top, and blue is below. But in this case, the color scale is different, but it's still fine. And why? Okay, hold on a second. Okay, it's only, why is the scale only 0 to 1? Why not -1 to 1? Just give me 1 second. Okay, the plot looks fine. Can you scroll up a little bit?
Maybe my code, because that's all I did.
Yeah, so energy underscore df1.core. Okay, core plot, that's fine. Scroll up a little bit.
Up?
Yes, I want to see what's in energy underscore df1.
Oh, what's in there? That's the
data set.
Clean, the clean data set. Yes. Dropping the
okay, I think maybe it kind of looks okay. Scroll down. I'll tell you why. Okay, so the first reaction that I had was that heating electricity kilowatt hour, right? That has no correlation with any of the variables, and that's what you can identify from the plus symbol here. Pretty much the black colored plus symbol, right?
Yeah.
That means zero correlation with every other column out there. Okay. And that also kind of might make sense because if you see gas facility kilowatt hour or heating gas kilowatt hour, both of them are correlated, right? So you look at so by the way, the diagonal will always have white color, right? The highest correlation, as I said, right? Like a column is perfectly positively correlated with itself. So the ones on the diagonal will always have the highest color. So right now white is almost like 1, right? That's why the ones in the center kind of almost everything looks white, right? The diagonal.
Yeah.
So column on itself will always have highest positive correlation. So that's okay. The heating electricity one has 0 correlation. Just probably, did you see the values of heating underscore electricity?
Oh, I think, that's the one with the, where is it? That's the one heating. That's the one like,
this one.
Yeah,
so it's pretty much 0 everywhere.
Yeah.
Right. And that's the reason why you have 0 correlation with every other column, because irrespective of what value the value in what the value is in the other column, the value in heating electricity column is always 0. That's the reason why it ended up with this kind of a symbol, right? So if a proper data scientist sees this plot, first question they will ask you is, what type of cleaning did you do that you got this plus symbol here, right? Which means that you assigned a value of 0 to every value in heating underscore electricity. So the entire column has gotten a value of 0 when you did the cleaning. Right? So if there were any real readings, they might have gotten wiped out.
Oh no.
Okay, so just check that once, that you didn't have any readings there.
Okay.
Yep.
Let me see. Is this the cleaning? I think
So
this is
let me also have a look at it. I have the code here as well, and I can clean it and clean the data like this. So technically, okay. So turns out there are 255,769 rows with 0 as heating electricity value.
Yeah, because this is this screen right here is like after cleaning and putting zeros, like this had none in them, but see, it just shows 0 and it
No,
still
this
shows
is
the other
heating
reading.
gas. This is heating gas, Susan. You have
So
to
which
look
one
at
were we
heating
talking?
electricity.
It's in
Go left. Go left. Go towards the left. Yeah.
Oh, this is a problem.
Yeah. So you see, there are zeros at most places, but you wiped out about 25,000 rows of information.
Wait, what? Why?
Wow, that's too much.
All I did was replace the.
Yeah, you now.
This is what I
Yeah.
did.
So
Oh, yeah.
it looks like what the operation did was just fill a 0 everywhere, from what I understand.
No,
or
but
okay, wait.
That doesn't
Also,
signify to put 0 everywhere.
Yeah.
Okay, wait. The question is, also what's the range of values that heating electricity has taken? So although there were 25,000 values, so the values look like they are between 0 and 1. I don't see anything beyond 1. Let me see that.
Yeah, that could be part of it.
Okay, so there are 15,000 rows with more than 1. That's good. 12,000 with more than 2. Okay, so there are some values. You got to check that. There are some values. So, but looks like it's tiny in comparison to the scale, right? So that's why every feature should be like treated individually. If you treat them all, put them all in a single scale, sometimes these are the issues that you might run into. Make sense?
Yeah.
I can show you
but you said heating electricity, right? Okay, yeah, please.
Yeah, heating electricity.
Why are you even using them when you just want to use the total one? So you can just remove
you can choose total as well, Susan.
Just use the total rather than disturbing yourself doing all this.
Yeah, I think this was just like doing EDA and just like.
No, you can use like for me anyways, I use just the total to do all the EDAs or whatever I want to do.
So by the way, scroll down, Susan. If there is anything else, let's see that, and then.
No, that's it.
That's it. Okay.
Ended
Gotcha.
here. Okay. But you said you wanted to come back to this
figure, right? Yeah. Just go to that figure once.
This one. Yeah.
Right here. Right now, on the right side, if you actually see, there are so many different types of buildings, right? Now, do you see as many colors in the plot? You don't. Right?
No, it kind of like blends.
Exactly. They're blending into it, which means that they are overlapping, right?
Okay.
So again, you don't know how these things are distributed unless you view each building separately. right?
Okay.
Now, I'd like you to look at, assume the blue one, right?
Which would be this one?
Yeah, quick
guess.
service restaurant, right? Again, we don't know because all the blues are right now probably overlapped, right? So when you plot it separately, you'll get a better idea. But in this plot, let's assume that all the blue points that you see are from quick service restaurant, right? What is your idea when you look at the blue points that you see on this plot?
So
Like Jude kind of mentioned a good point.
Yeah, so it looks like this quick service places most likely are in Chicago because it looks like they are using more gas.
Why do you say so? Why in Chicago?
That's the point Jude raised. Like Chicago uses gas over electricity.
Yeah, but in this case, we don't know if it is Chicago or not. It will just be that they use more gas.
Correct.
Than any other
So without
building
saying,
type.
Yeah.
They use gas, more gas. Yeah.
Yeah, that's the correct interpretation. That we just know we don't know the location yet because we don't have any markers to differentiate the readings between Chicago versus Atlanta, right? But what we do know is that quick service restaurant uses a lot of gas. It's one of the highest gas consumption places or building types. And you see the electricity is also there, but it's kind of like in a stable range, and it has a peak. It has a peak and then it comes back. But gas is super high. And think of a McDonald's or a KFC or something like that, right? Those are the quick service restaurants, right? So if they are frying sausages or patties or chicken or something like that, right? So they'll be using gas almost pretty much the whole day, right?
Yeah.
And that's the reason for the high gas consumption.
Okay.
Right. So what else is there? So like this, what you could do is for each, you can separate out these visualizations. For each building type, you can get a visualization. And there are nice interpretations that you can get from those visualizations.
That would be like too much.
Yeah.
Yes,
no, so I think
you could do for a couple. You could do for a couple. You don't have to do for everything. You could do for a couple and say that, hey, there are like 15, 16 different types of entities here. So I'm doing the interpretation for 2, but we can drill down the analysis further on a specific business building type.
Okay.
Right? Make sense?
Yeah, it does. Yeah, so I think I'm just gonna, because the EDA, I feel like it gets overwhelming trying to like just go through each one. So especially now that this is giving me issues, like the filling it with 0, I'm just gonna stick with the totals and then do the EDA
Maybe,
of the total.
so do one thing. So scroll down, Susan. Scroll down, I'll tell you something. Where's your final data frame? Energy_df1, right?
Yeah. Where is it?
So just open a new cell, code cell, write energy_df1.
Okay.
Take a new cell. Do energy_df1. Paste it. Do square braces. Inside that again energy_df1. Again square braces. And then double quotes. Now copy from the bottom, right? Like from the bottom output, copy heating, just the bottom one. You don't have to scroll down. Just copy heating_electricity, that piece. Remove the space from the starting once you paste it.
Okay.
Yeah. Now, before the last square brace, go inside. Yeah. Over here, place zeros equal to.
So
double
0
equal to 0. No, equal to 0.
Like that.
Yep.
Okay.
And execute this.
What is this doing?
You should tell me what is this doing.
I don't know.
You are getting all the zeros.
Oh, it's showing me all the zeros.
It will show you the data frame that has all the zeros. So scroll down a little bit. Look at the bottom of the output that you got. Okay, so there are 25. Yeah, that's the right number. 255,769 rows with zeros. Now go back up.
Oh.
So what this condition is, so you have a conditional statement, a condition inside your braces. So it is filtering energy underscore df1 data frame using that condition. Right? So it shows all the records that match this particular condition. Okay. So wherever heating underscore electricity column has a 0, it shows you all those records. Okay.
I see.
Now we can do one more thing. Put one more row, create one more cell.
Okay. So does that mean like is this the same result you got for when you checked?
Yes. When I checked zeros, it's the same result, which means your data is still there. It's just that the scale is not appropriate. So just do energy underscore df1. Yeah, the same thing. Then do square braces and then quotations and put heating into that.
Oh, so the same thing as this?
Yes. Not the whole thing, just the one inside.
Just from here.
Yeah, here onto energy. Yes. No. Just until the first energy one.
Oh, like this. Oh, good Lord.
Control Z.
Control Z.
Yeah. Yes, just until there. And then you should remove the initial square brace that you copied. Paste it here. Remove the square brace in the starting. Remove the square brace in the starting.
Okay.
Dot unique. And then parenthesis, close braces. Parenthesis actually, brackets, curly brackets, not curly. What is that? Round brackets, parenthesis.
This one?
Not that.
The other
function
one.
call. Function call. Yeah. Like the one in info. Yeah, that one.
Okay.
Just do control enter now. This will show you all the unique values that column will take. So there you see that these are all the unique values. Now, if you do len, and then put the everything that you wrote over there, it will tell you how many unique values are there in that column.
What am I doing on here?
You're basically looking at the various values that are there. Now, if you see, all the values are like 0, 0.11, 0.25. Some of them are 2s, 3s, and so on. But
this is what you're looking at, saying, oh, you don't have more than...
Correct.
Okay.
Correct. So let's say I'm looking at something beyond, say, 50. Okay. There are some values beyond 50.
You want me to stop sharing screen?
No, that's okay. I'm trying to see what's the limit. $273. So 273.64 is the highest value that column is taking. So it looks like there are about 25,000 rows which have heat underscore electricity available. Rest of them don't. Okay. So rest of them are zeros. So it's not great to not use those 20, and you're not taking them away. You still have them. Looks like you still have them, but because your scale is so huge that you're going all the way to 4,000, the maximum value that this column is taking is 273. right?
So the scaling is the issue. Is that what that is?
Yeah.
Well, that's the only way I could get this to actually look half decent. Like if anything smaller than this, like you could barely see like the boxes.
I didn't understand. If you did you try a separate plot for each of them?
Oh no, I didn't. I guess maybe that's
Yeah.
where, yeah.
Just
I
do a
mean, like,
separate plot. I'm pretty sure it will show you
it will
better
look better.
distributions than this. Yeah,
Okay.
for sure.
So my final question is, this is like a lot, like with the EDAs. So if we decide we're just doing the totals, do we then keep like doing the
No.
No?
No.
Uh,
I would say, I mean, see, because that's a choice that comes after studying your data. This is
Okay.
a study of your data. EDA is basically exploratory data analysis. We are studying your data, right?
Okay.
I mean, if you want, you can skip, but
Don't do
this
it.
is what you would do when you are working,
Okay.
right? Because you will simply say that, okay, since I'm not doing it, and you want to get things done quickly. Right now is the time when you guys have time. There is not like, I understand you still want to get launched as soon as possible, but put in the effort, do as much as you can to learn.
Okay.
Right. So, and see, because when somebody comes and looks at your project, they need to see a lot of visualizations. They need to see a lot of analysis that has gone into it. Right.
Okay.
If they look at your project and then if they ask you a question, why did you choose the aggregates? Why not the individuals? Right.
Oh, yeah. You should be able to
You need an
answer
answer.
that, like...
Exactly.
Okay.
Right. So you have to analyze these things. It's good to have these EDA. And so I would say,
Well, how many plots is enough?
I
mean type of plots.
I would say, as per my requirement on the DS project instructions, at least 3 plots. Right?
Okay, so 3 types. Okay.
3 types of plots, right?
Okay.
So have at least 3 types of plots, but try and do as much as possible if time permits. So what you guys can do is like do 3 types of plots now, have them ready, and then later if you have time, add more.
Okay.
Make sense?
Yeah, it makes sense. So right. I don't know. If this Bowling plot, I don't need to do that, right? Because
so if you get your box plots right, you don't have to do Island. Okay. And correlation is also part of EDA.
Part of it. Okay. All right. Awesome. Okay. All right then. Okay.
So Jude, you can share your screen next. And we need to quickly do a review of last class's concept, PCA, and then start with the new concept as well. And I guess I hope you guys have logged into the Colaberry app so that you get attendance. The others who joined, Liz, Jude, hope you guys joined and you got your attendance.
So from the EDA, this is the only one I think I did, all of the data, even though I've not done cleaning and all that here. I'm supposed to remove all this one here, but yeah. So, but for me, I just remove everything, and since we only need the month, the total, so I decided to use all of the totals right here. So I remove all of them and just use the total one like that. So I did the first one. The electricity facilities box plot looks like this. You can see the outliers right there. But the data is still like some percentage, maybe 70%. The gas, so the gas, you can see there's so many outliers and
gas. So the thing is, the spread is very less. See, okay, this is one question. Let me ask you this. So you see this box in the electric underscore facility, right? And this wide box, right? The box in electricity is wider. The box in gas is like very thin, right?
Yeah.
Can you guys tell me like how many data points are there in each of these boxes approximately?
Like staring at this
number, the number of data points.
Number of data points. Like 70%?
Sorry?
Like 70%?
70%?
In
No.
electricity?
Just the box. Okay. In electricity, you're saying 70%.
Yeah.
70% of what?
Like it has more data. Like if you say out of 100, it has more data. It has more 70% data.
Okay. Let's assume, so the total number of rows we have is 280,000, right? So how many number of data points does the box have in electricity?
It will be around, let's say, 200,000.
200,000? 70% of 280,000. That's the idea, right?
Yeah.
Probably. Okay. Somewhere 200,000 plus something.
Yeah.
Basically 70% of the entire 280,000. What about gas?
That would be like 30.
30%?
Yeah.
Okay. Now here's the point. Both of them have the same number of data points in those blocks. It's 140,000.
How can you tell that?
Because box plots, they are plotting all the points that are there. So you have 280,000 total number of points, right? In the box plot, the interpretation of a box plot is the box starts from 25th percentile data, extends all the way up to 75th percentile data. That's what a box plot's box is, right? Now 25th percentile to 75th percentile is 50% of your entire data, which is about 140,000 rows of data. Now, no matter where you apply the box plot, as long as you are applying it to the same data frame, right, but different column, which means the same number of records that are there in both the, both the plots that you see, electricity and electric underscore facility, gas underscore facility, right? So the top box also has 140,000 points in it. The bottom box also, the tiny box also has, the narrow box also has 140,000. Why the difference? It's because electricity is more spread out in terms of the values that it takes. Gas is not as spread out. It's all very concentrated in a very small range compared to the scale that is there, right? So in gas, for the column of gas, right, you have a scale of 0 to 4,000, right? Now, if I have to talk about, give me 1 second. So if I have to talk about the range of my gas column itself. Yeah. So for gas, right, the top 75th percentile value is 83.98. So roughly around 84. The 25th percentile value is 2.1. So all your data for gas, right, it lies between 2 and 84, right? That 50% of the data, 50% of your entire data lies between 2.2 and 84, roughly. And the rest of the data that you see, right, like the other 140,000 rows of data is spread out from probably about like 200 or wherever that is, and all the way up to 4,000. The top value is 3,886, 3,986 or something like that. So that's your gas column. So which means that tiny box that you see between 2.2 and 84, there are 140,000 records of data. With respect to electricity, right, and given the range is 0 to 4,000, 2 and 84 is a very tiny range, right? That's why you see it as such a small bar, right, on the bottom. Now, when you compare that with electricity, let's see what happens. All right, in electricity, what are these specific values? So you have 25th percentile is 26 roughly, and 75th percentile is 225, almost 226. So 26 to 226. That's the range, right? So that's considerably a larger range, and the scale is smaller in the top graph. Jude, are you getting that? Scroll up a little bit, just a little bit. Yeah. So you see here, the scale is only between 0 and roughly about 1500 or 2000. And the box, the range of the box is much larger than something that is between 2 and 84, 2.2 and 84 on a scale of 0 to 4000. That's the reason why the bottom box looks tiny or much squeezed up, and the top box looks a little bigger than that because the scale is smaller. That's why it looks a little more widespread. But basic interpretation is that this box plot basically plots all your information, and then the box starts from 25th percentile of your data to 75th percentile, right? So this is 50% of your data, which is 140,000 rows. Now the top box, bottom box, both one box might be narrow, one box might be wide. That basically tells you about the distribution, the range in which the values are spread out. So gas facility has a narrow range of 2.2 and 84. Electricity has a larger range of 26 and 226. Makes sense, guys? But the number of points is still the same. It's 50% of your entire data, entire 280,000 records, which is 140,000 records. Make sense, guys?
Okay.
Clear? Liz, others, have any questions?
Nothing.
So just to be clear, so the box itself has all the data in there. It's just the scale is different, right? Between the electricity and the gas.
Yeah.
We're still looking at the same box.
No. You're not looking at the same box. You're looking at a distribution of these values.
The same. Okay.
Right? But the number of records that are making that box in both the graphs is the same.
Okay. So the number is the same.
Yes.
But the data distribution is different.
Correct. Absolutely. Which means the range of values is different. Right? Yeah. The range of values is different. So, but if you see the number of data points that are contributing to that box, it's the same in both the, it's 140,000 records of data, right? It might be different 140,000 records of data, but the number is same. So half of your, so electric underscore facility, right? That column has 280,000 different values, right? In the data frame. Among all those 280,000 different values, 140,000 values make up this box, right? In the same way for gas facility as well, 280,000 different values are there. Half of those values make up that tiny box.
Okay.
It's just that for gas facility, all those 140,000, half of its values are between 2.2 and 84 range. That's the 25th percentile and 75th percentile range,
okay.
Right? For electricity, those same half of its values lie between 26 and 226. So 25th percentile of the electricity data, so 0 to 25% of its data, right? The first 25% of its data is less than 26 in value, right? The next 50% of its data, 25th percentile to 75th percentile, lies between 226 and 226. Then above 226, another 25% of its data is spread out. This is with respect to electricity.
Okay.
Awesome. Scroll down, Jude. Let's see if there are any other questions.
So this one, I actually wanted to do like a time series graph, but we do not have like, I was trying to make the date time, like the index so that this could work, but that doesn't actually have like a year. So, so it's messed up.
Gotcha.
I'm not sure this actually makes sense, but
yeah.
You know.
It's a challenge to you guys, but it'll be fun to solve. So see all of these ratings, right? I think it's a 1 year data or 2 years data. It's not more than that. If you look through the data set, the source of the data set, you'll see it's taken in, I think, 2012 or something, these readings. Okay. So look at that year, you can plug the year, and once you plug in the year, what you can do is just, or even if you don't plug in the data, assume that it's of a certain year. right? Assume for
okay.
the purpose of your analysis, and then attach a specific year to that, right? You will get get these
That's the
readings
time.
out,
Okay.
right? Get the time, and then convert that column to date time,
Okay, I'll do it that way.
right? Once you convert that into date time,
So
then
I
you
can
use it.
just use any year that I like, whatever, just for the.
Yeah, so make sure that you state that assumption. So tell them that,
Okay.
hey, I'm assuming, I don't know what the year is, so I'm assuming that it's this year. Or I would suggest just look at the source data once. I'm pretty sure it'll be there somewhere. I think it's 2012. I'm not sure. If I find it, I'll let you know. Okay.
Okay.
Yeah. Scroll down.
All right. So that's why that one is there. All right.
Yeah.
Then I try to like find. So this is the
Box plots.
location part where. So this is where I think that gas is more used in Chicago than in Atlanta because of the way the distribution is, even though
Okay, got it. You can't say more used, but what you can say is the spread is more, definitely, right? Which means there's a lot of variation in how gas is used in Chicago than in Atlanta.
Okay. Yep.
Right. That's definitely, that's something that you can definitely say.
So there's a more spread of more use of gas in Chicago than
variation, right?
There's variation of use.
Exactly. Which means that maybe Chicago downtown has high usage, right? Has higher usage rather than Atlanta. And why is that? Can you guys tell me? Why do you think so?
Gas, because of cold.
They use gas.
Because of the cooler region, right? Like Atlanta is down south as compared to Chicago. Right?
Because
so that could
cold.
be exactly. And that could be your explanation, because also if you see, it's on the same scale, but Chicago might even start at the same level as Atlanta, but it goes above, goes higher. Right?
Yeah,
so the
I
variation,
still have explanation down that will show that because of cold and all those things. So plots, this one is the one that is it looks somehow because the building can fit in, the names of the building can fit into this. I don't know how to spread it differently. So
yeah, the better thing to do is just do it one for each building type.
Yeah, I'll just remove it. I just remove it. There's no.
But the second plot looks good. The electricity one, right? Okay, that has a lot of variation, and the reason why.
I just remove it. We don't have to show that. So then the next thing I did was
actually, you know what, guys? Jude, I would like you guys to keep this and explain why this would not make sense, right? I mean, this is a personal request. Technically, you don't have to do it. You can remove it. But the only reason why I'm saying that is anybody for the future batches, right? When somebody is looking at it, they can learn that why such a visualization is not good, right? Learning from mistakes or learning from something that's bad, not just learning what's good. Make sense? Yeah, so keep the thing, but make sure that you write explanation saying that there's not too much variation. That's why this graph just doesn't provide us any visual cue.
Okay, but what if you keep it and somebody else saw it and did not read what you wrote on it? They will just say, these people don't know what they're doing.
So then you have to point them to the interpretation that you wrote and tell them that, hey, read it. Before you comment on me, read it. Right?
Okay.
I know that it's bad, but I kept it because I want to show you what's bad and what's good.
Okay, I'm going to point out. I know it's bad, but I just want to show you so you can learn from it.
So the reason is, because when you put this out there, right, like the step-by-step instructions and stuff, so you can remove it from your presentation. Don't keep this in your presentation, but keep it in the step-by-step instructions just to help your juniors, so to say, right? People who will join this training course post your batch, they get to learn from your experiences.
Okay.
right? That's the only reason. Don't use it in your final analysis. Don't say that, hey, this is my dashboard.
Okay.
That's bad.
Okay, so the next one is to get the mean of the building.
Okay.
So this actually worked well because it didn't list all the buildings. So it just show like the distribution of how electricity is being used in each building in both locations.
Yeah, this is also again a good plot because you kind of can clearly understand, and this is mean electricity, right?
Yeah.
So how did you calculate the mean? Just go up. I wanted to see.
I just did aggregate mean.
Okay. Okay. Yeah, you could do that too. Or you could simply use the mean function. That's also there.
I like to use the simplest one that I can remember.
Sure. Mean is even simpler, right? You don't have to use aggregate in the past.
Yeah.
Just do mean brackets. That's it.
The one I can remember quickly. Yeah.
That's fine.
So
but this is a good plot because this can tell you where you will see a lot more consumption, right? As opposed to something else. So standalone retail, right? Look at that. That's like rock bottom almost.
Yeah.
Right. Quick service restaurant also is like less electricity because they don't care too much about ambience. Now, if it's a full service restaurant, right?
Yeah,
they use upscale. Yeah, they have chandeliers, lighting. Yeah. So
these are the explanation.
Yeah, but surprisingly, large hotel is.
It's still part of it. It still uses more because it's right here.
But I would think large hotel should be comparable to full service restaurant.
But large hotels don't really use much light. If you look at it, they have rooms. If the rooms is not occupied, the lights are off.
Yeah, that makes sense.
The lights are off. So yeah.
That's awesome. That's good. Scroll down.
Then this is for the gas. So I did the same thing for the gas too. It looks like food service restaurants use more gas.
Yeah.
So then I decided to remove the date and time. So I did like the monthly mean for each of them.
Yeah.
So that's where you see that in this part from May to like August, they use more electricity. So which is the summer.
So how did you calculate? Okay, you aggregated by month.
Yeah.
Perfect. Okay, that's good.
So electricity is more used in the summer than during other months of the year.
Awesome. Scroll down.
Then the gas too, you can see less gas during summer too. Cool. High gas during winter. So
cool.
Like that.
Scroll down.
And then what did I do again? That's just the box plot to show like each month how how you use gas.
Scroll down all the way. That's it.
This is the time.
Okay.
The time variance of gas. So how gas is being used. So it looks like.
Why box plot for this?
I just feel like using box plot.
Yeah, don't use box plot for everything. Box plot is just for distributions, right? For a specific feature.
Yeah, I can use the line graph.
Bar, line, yeah, you use something else. Okay, all right.
So
okay, well, good job, guys.
All right, one more thing.
Yes.
So,
stop there. Go up. This part. Yeah, I want to see this before we proceed to. I think you attempted modeling, I guess. Let's see that. But before that,
I only used two of them, so that's why I could get the 0.5 and it is 0.5 to 1.
Gotcha. Okay. Decent. 0.45 means a little bit of correlation. Not strong. At the same time, it's not zero correlation. There is some correlation. Okay, that's fine. Scroll down.
So
Liz, you can drop off. I'll share the recording later. No problem.
So this, I try to use, since it's, the location is important, so I try to put the location on the features, and then try use I encode the building. Then I use that as the target, which I mean, I don't feel.
What did you use a target? Come again.
I use the building type as the target. Since
Building
we are trying to
target. What are you trying to do?
And we are trying to forecast the total amount of energy used in all these places or in all these buildings. Is that not what we want to do?
Correct. So then what is the target?
So the building is the target.
No. What are you trying? Come again. What are you trying to predict?
Forecast the energy consumption.
Correct. Forecast energy consumption. So it will be either electricity or gas or a combination of both. That is your target. That's what you're trying to predict. What are you predicting in based on location, based on building type, based on time of the day or month of the year or something like that. Right? Regression. Right? Regression is where you're predicting a number, not a category.
Yeah, but we changed the category to number.
Yeah, I understand that you do because you are trying to feed the category to your model, right? But okay, you are trying to predict location. So like, how does that help you forecast the energy consumption? What's the interpretation there?
That's the reason. That's the place where I'm so confused, because I was thinking, how can we even use building as a target? Because it doesn't make sense to me. But that's why I just did it so I can show something in class. Because of that. But it really doesn't make sense to me, and I feel like electricity, facility, and gas are the main features that we are trying to use.
Predict.
Yeah, we're trying to.
Those are the things that you're trying to predict, right? And the patterns are hidden in the data based on the location, based on the building type, and based on, more importantly, also based on time. So this prediction is a time series analysis, Jude. That's something that you have to recognize, right? Because there is a clear pattern in, like, let's say full service restaurant. You're taking a full service restaurant, right? At each time, right, of the day, there might be a different electricity consumption. The restaurant is probably closed at like probably 11 a.m. in the night, and then it only opens at like probably 11 a.m. in the morning, right before lunchtime. That's probably how a full service restaurant works.
Yeah.
So you'll have zero consumption from 11 p.m. to 11 a.m. Right?
Okay.
So, and then there'll be like at 11 a.m. when there's a peak, right, in the restaurant. That's the lunchtime, right? So a lot of prep work is going on. So you'll see a lot of gas consumption, you'll see a lot of electricity consumption, right? And everything goes on. And then post 3 p.m., again, there might be either the restaurant might close off or it might be open to very little people. There'll not be too many people coming in. So they might not use, turn on the lights. They might turn off ACs at some place. They obviously won't be cooking, right? For dinner time, they'll start cooking at about 4:30 or 5 o'clock. That's when the prep time starts, right? And that's when, again, the gas consumption and electricity, everything goes up. So these are like clear patterns in your data, right? Make sense?
Okay.
So it's a time series prediction.
Yeah.
It's a time forecasting is a time series prediction.
That's why I was so confused, because first and foremost, we don't have the year. And it's just electricity and gas. And so I was really confused, but I was like, okay, let me just try and do something. Maybe discuss it in class. So you're saying now that I have to either use electric and gas together?
Or
as the
one of them.
target?
Or
If I
one
use,
of them.
if I use one of them, what else will I use the other one for as the feature?
No,
Because
the
it
other
won't
one
make sense.
will not be a feature. It won't even
Yeah.
be there in the
Okay.
analysis.
Yeah, because it won't make sense. So I can use
Yeah.
both. Okay. Yeah. Okay.
So you are either trying to predict the combination, the entire use of electricity and gas, or you are trying to predict the electricity, or you're trying to predict gas. Don't try to, don't try to use the other one that you leave out as one of the predictors. That wouldn't make sense.
Yeah. Well,
okay.
Okay. So
the correlation plot, when you go up, right? You should look at, you should put in, do that. Yeah, you don't have to put in, I guess, because it wouldn't make sense. So yeah, these are the only two numbers that you have. There's no other number. So yeah, just forget about the correlation plot in your case.
Okay. So the time series now, because right now I did like I removed like the month, the day, and the time. So can I just put them into this right now, or I should combine all of them together as date time?
It's a good thing to have them as month, day, I would say, right? It's easier for you to process. Okay, you like can keep it as a single column, but if you do so, in your predictors, what you have to do is you have to extract the month and day based on the column name. It's better to just keep them as separate columns and then use however you have it right now, right? Time, month, day. Just use that. It's probably easier, better.
Okay, so I can use that like this as a feature.
Yeah.
Okay. Now I get it. Okay, yeah, that's all I have. That's it.
Okay, yeah. So, but one thing, so here's one aspect that I want to clear. When you build, let's assume that you're splitting it, right? Time, month, day as three features as opposed to single date time feature. Okay. What happens then is, in the prediction part, like once you build out the model, right? Let's assume you gave it a timestamp instead of giving month and day, or let's assume you gave timestamp and also gave month, but you did not give day. So you are missing one or the other columns, right? The model might not be able to give a prediction.
Okay.
Right. So, okay, wait. But in this case, you have to split. You should keep time, month, and day separate itself. Because one problem is, oh no, you can keep them away. Oh, okay, one more thing. It's a little confusing for me or anybody to look at your code. Reset the index of your data frame, because the last row shows 8,759, but that's just the last row of the last file that you bought into your data frame, right? So when you reset the index, you will clearly get all the 0 to all the way up to 280,319.
I do not understand. Is it like the total number of rows?
Yeah, so your index, right, on the left side, 0, 1, yeah, it's 8,700. So do you have 8,759 rows? No, right?
No.
You have 280,000. Because somewhere what happens is that 0 goes, stops, and then a new 0 starts.
Oh, okay.
Because you stitched each file, right? You read each CSV file at a time and then added it to the data frame.
Yeah.
So at the end, you did not reset index. So when you do .reset_index on your data frame, right?
Oh, okay, right here.
Yeah. So that will clear things up.
So I need to do, let's see.
Okay. Cool. Anyways, good stuff. So I think it's fine if you retain, because you have data across. So one thing I was worried about was, if you had the date time as a single column, then there would be like 1 year's values, let's say 365. And if it's all unique values, then it will be an issue, is what I was thinking. But this is data across various locations. So that's how the variation comes. So don't bother about it. So you can take either the data in a single column or take it in 3 columns and use that. It's either thing is fine.
Okay.
Okay. But just note that if you have 3 columns in the test set, you need to mention all the 3 values in order to get a proper prediction.
Yeah.
If you miss something, right? If you don't mention hour or don't mention month or don't mention day, you can't get a prediction. Okay. Yeah.
Okay. So you say I should reset like this?
But no, not that. So you have the data frame, right? So
yeah, this one.
energy underscore professor underscore ds df dot reset underscore index.
Oh.
And in braces, inside the braces, you do in place equals to true. In place equals to
true.
T capital.
Oh, capital.
T capital, because it doesn't recognize as a keyword otherwise. Yeah. And then click on that, click there.
Click it?
Put an enter. Don't run, put an enter. Okay, that's fine, that's okay. Now create a new cell and see energy underscore, see the data frame. View the data frame.
Okay.
But here what will happen is the index will form a new column. The old index column will form a new column. Old index values. So yeah, so you have the new index which says 280,319, right?
Yeah.
But the problem is the old index values are now put up as an index column. So you have to drop that column as well.
Oh, drop this column.
Yeah. And then you will have nice index.
So I'll have to
dot drop.
Yeah, but will I say the second one?
No, so dot drop, then open braces, columns equals to square braces, index, all of that stuff, like how you did in the bottom, right?
Oh, like, right. Oh, wait, let me see.
That's rename, but yeah.
Yeah,
but the rename is like map, it's a dictionary. This one's just a list. So columns equal to okay. By the way, guys, it's been quite some time now. I have to refresh the concept from last class and also start the new concept. So we'll take a break. We'll be back and then we'll start the new concept. But before going on a break, I want to talk about PCA. Jude, you were there in last class? Yves? Can either of you, Yves or Jude, can you guys explain PCA from what you understood in last class to Susan?
PCA is principal component analysis. So it's like, it's not really like what's the last one that we did first?
K means clusters.
Clusters, yeah. It's not like the clusters ones. All you have to do is, it's like reducing like the number of variables, something like that we want to use.
That's good. But how does it work?
That one I can't remember.
Okay. So let's go over it, Susan. So since you were not there in last class, and at the same time, we do this recap all the time. So just let's go over how PCA works, principal component analysis works. Let me, before sharing my screen. So Susan, so when you drew the correlation plot in your case, right? So there were what about like 14, 15 features, right?
Yeah.
13 features, 13, right? So 13 by 13 or 11 by 11, 12 by 12, whatever. That was the matrix you got, right? Now, assume your data set has 60 features, right? So your correlation plot is going to be a 60 by 60 grid, right? And that's going to be like extremely difficult to see each and every cube, right? And then determine, okay, what color is it? Is this positive or negative correlation? Should we keep this variable? Should we throw it away, right? You get the idea, right? So that's the challenge with high dimensional data. When your data has a lot of columns, right, that tends to be a lot of information for the model to process and for you to process as well. As if you're trying to manually select features based on a visualization technique like correlation matrix, it becomes extremely difficult. And that's the reason why you have something called as PCA, which is principal component analysis. It's a dimensionality reduction technique. Okay. That's why it's different from clustering. It's not your clustering stuff, but it is still unsupervised because you don't care about your target, right? You apply dimensionality reduction to your predictors. First, you apply your dimensionality reduction to predictors, convert 60 columns to about 6 or so, and then you use those predictors to do the next supervised classification model, right? So you either end up doing regression or classification or whatever, right? But here, what you end up doing is, right, before that, in dimensionality reduction, you don't care about your target variable. You're just taking your set of columns and converting them into a shorter number of values. And the way you do it is by eigenvalue decomposition and eigenvalue, eigenvalues and eigenvectors, right? So in DS2, you guys have studied about eigenvalues and eigenvectors and eigendecomposition, right? That's exactly what happens with PCA. And that's the reason why we included eigenvalues and eigendecomposition in DS2. So let me quickly share my screen and explain things to you. Yeah, and this is what I did in last class as well. It's kind of the same example, right? So assuming I am trying to, the same old example, right? Like the price of shirt. Let's say I'm trying to predict the price of shirt based on 3 variables that I have: the cost of cotton that I am purchasing, the labor cost, and the equipment cost, right? Now, in last class, we kind of analyzed and thought that labor cost and equipment cost are inversely proportional or inversely correlated, negatively correlated, which means if my labor cost goes up, my equipment cost might go down because I have a lot of people, I don't need much equipment. Or my labor cost goes down when my equipment cost goes up. Let's say I bought a lot of sophisticated equipment, which doesn't need too many people, which does a lot of things by itself. So I don't need to employ too many people, right? So the labor cost goes down. That's the negative correlation. And we kind of also established that cost of cotton and cost of equipment might actually be positively correlated, where, the higher the cost, the grade of cotton, the quality of cotton, that will result in the higher price of cotton. But in order to process that high quality cotton, you might require high quality equipment, right? Or low grade cotton might actually be processable in a low grade equipment as well, right? So based on those assumptions, we kind of looked at this 3x3 correlation plot, right? Where we thought, okay, this cell will have red color, this cell will have white color, this cell will have close to blue, close to red, and so on, right? Now, what will happen if I have 9 features? I will have a 9x9 matrix, right? It will be difficult. So I use PCA. Now, PCA has about 5 different steps. It first standardizes all the features. Then it converts all of them like to some other format. It normalizes them. Then it looks at eigenvalue decomposition, so on and so forth, right? So that's how PCA as a technique itself proceeds. But how it works is, I have 9 columns here, right? These are 9 different predictors. Now I don't have my target variable here, right? The column that I'm trying to predict, the target that I'm trying to predict is not here. Okay, it's the 10th column or the 11th column, whatever. So I'm just looking at these 9 predictors here. These 9 columns, I will construct, when I apply PCA, it constructs something called as principal components, right? Now PC, the first principal component, might be a mixture of, or a combination of these columns, might be a combination of columns 1, 2, 3. The second PC, right, might be a combination of 4, 5, 6. The third PC might be a combination of 7, 8, 9, right? But you see 8 is missing here, right? Now, why is 8 missing here? So when you apply PCA, what happens is, and this is something that you have not removed. The model itself, when it's building its principal components, it rejects certain existing columns and it picks combination of the remaining columns that it keeps. How does it pick columns? How does it keep columns, right? How does it discard columns? So let's assume that column number 8 has all the values between 0.5 and 0.6, which means low variance models, right? Low variance column. Susan, are you following so far?
Yeah.
Right. Okay. So just now in your box plot, you've seen that gas or something was like very low, right? Like the variance is very low. It was like squished, right? Or in fact, heating electricity, right? Because we had such low variance, a lot of 255,000 zeros and then 25,000 values, which are like very tiny, right? You had not much variation in that column. And that's why you saw the correlation was neutral, right? The black stripes, if you remember.
Yeah.
Now, what will happen is when you apply PCA to that data set and it discovers that, okay, my variable, this variable is not being affected by anyone, it's not affecting anything, right? So it has no variation. So whatever value this might take, my target won't change, right? Because there is no variation for that particular column, right? It has very tiny set of values and it doesn't change much. Even if it is changing, my target and my other data points are not really affected too much by it. So I will throw out 8 because it's not useful for any predictions because it's not affecting. A change or no change in this particular variable is not changing any of my other variables and my target. Make sense?
Yeah, so but the PCA does this, you don't.
Yeah, you don't have to.
Okay.
It's how it works on the back end.
Okay.
Right? So it throws out 8. Now, how does it even come up with the first component? Let's assume first principal component. How does it come up with, hey, I need to combine columns 1, 2, 3, or I need to combine columns 1, 5, 7, right? It will come up with a combination of columns. A mixture is what we call it. Now, how does it come up with this mixture? It look at the columns or the features which have highest variance, right? Which of these have like a big range? Like, let's say my lowest value is 2 and my highest value is 2000, right? And there are lots of values in between. And the box is like, when you draw the box plot, you get the wide boxes, right? It look at those columns, the columns which have the highest variance. It will combine those columns as this is my first principal component. Once it combines these specific columns, then it will move and say that, okay, second principal column component. Then it will pick all these other features, let's say 4, 5, 6, or maybe 4, 9, 11, or something like that. Some other columns, a mixture of those columns, combine them, and then say that, okay, this is my second principal component. Okay, like that, it comes up with principal components. And once these principal components are constructed, basically these are matrices, right? These are eigenvalues, eigenvectors. That's basically what comes up. Instead of using 1, 2, 3, 4, 5, 6, these columns in your prediction model, you will use first principal component, second principal component, third principal component. You will use the principal component values, which is the eigenvalues, eigenvectors. That is what you use as your predictors, new set of predictors for your target variable in the next task. Make sense, Susan?
Yeah.
So what did you do? Effectively, instead of using 9 different predictors or 9 different columns, you ended up converting or transforming those 9 columns into 3 combination sets, and you use these 3 combination sets as new features. So instead of using 9, you're using only 3. Right?
Yeah.
But those 3 have information from all the 9, or at least what's relevant. Make sense?
Yeah.
So that's how basically principal component analysis works. And there's a very nice article which tells you about each step-by-step process of what happens in a PCA. I posted it on Colaberry chat. Please read that. So the first 2 techniques that you guys have studied, the k-means and db scan, both were clustering. Last technique that you studied in just now was principal component analysis, which is a dimensionality reduction. Now we are back to the final concept in DS3, which is again clustering. Okay, so if you guys remember k-means and db-scan, the goal here is basically the same. You get groups. You get to group your data in a certain fashion, right? But what's it with hierarchical clustering, or what is basically agglomerative clustering in hierarchical clustering, right? Now, hierarchical clustering is basically it starts off with like 1 to kind of data points, and then it kind of, again, it's the same concept, but it has a specific hierarchy, which means that in case of k-means or db-scan, one cluster to the other cluster, there might or might not be any relationship, right? So if I have to like try to explain that, in terms of like k-means, right? You have these points, right? And let's say there is another set of points over here. That's a brown group and this is a green group, right? When you're building these things, right? Like if you guys remember how k-means works, right? Or even db-scan to that matter, each iteration, a specific point is picked and it is assigned to either cluster A or cluster B, right? Now, when it is being assigned to cluster A or cluster B, and no matter, like, we can choose K, right? We can choose to create 2 clusters, 3 clusters, or we can choose to create up to 10 clusters in this particular data set. Now, when you have like 2, 3 or these kind of iterations, let's say I want 4 clusters. Okay. Now this will be one cluster. This could be the other part of the cluster, and this could be number 3 and number 4, right? 1, 2, 3, and 4. Okay. Now, can you guys tell me if there is a relationship between 1, 2, 3, 4? No, right? Because this is one group, this is another group, these are 4 different distinct groups, right? But with hierarchical clustering, what happens is, like, let's say I have 1 cluster or 2 clusters in the data, A and B. And let's say there are some other clusters, right? Or some other, groups. So at any point of time, and this is the beauty, it's not just at the end of the process, but at any point of time, let's say 2 points are there in my cluster here right now that are marked as A. These, if A grows in the future, if A grows into a 4-point cluster, these other 2 points will always be a subset of this group. So there is a relationship between one iteration and the other iteration. In k-means, when you're doing these iterations, when you're growing clusters, there is no relationship. And that's the reason why it's called as hierarchical clustering, right? There is a hierarchy that is set in place that, clusters at a certain level are either supersets or subsets of a different cluster, right? And also another reason why hierarchical clustering is called so, hierarchical clustering basically has 2 approaches. First approach is top down. Second approach is bottom up. So top down is where you start with the entire cluster, right? All the points as one super cluster. We'll say that, okay, I have only single cluster, one big cluster. And then you start breaking this cluster off into pieces. Then you will say, okay, now instead of 1 cluster, I have 2 clusters, right? And then you will keep breaking things. That's the top-down approach. Bottom-up approach is wherein you will say, I will start with 1 point, right, as my, or as each point as a different cluster, right? And then I will keep combining, okay, these 2 are near, so this is 1 cluster, these 2 are near, so this is 1 cluster, these 2 are near, these 2 are near, these 2 are near. Like that, it will keep adding points and then keep growing clusters, okay, until it forms one super cluster, the entire cluster. So like how for k-means, what we did was we started from 2 all the way up to 10 or whatever number we chose. Here what happens is, if n is the total number of data points that I have, it will start with each individual point and go all the way up to one super cluster. This is the bottom-up approach. Starts with n, goes all the way to 1. Top-down is starts with 1, goes all the way to n data points. Each point is split as its own culture, its own cluster. Make sense?
Yeah.
So in k-means, it stops when all the data points are labeled. Similarly, in in hierarchical clustering or agglomerative clustering. Now, agglomerative clustering is a type of hierarchical clustering which is bottom up in nature, right? So it basically starts off with every point, treating every point as a individual cluster, and then it starts clubbing things together, right? It starts saying that, okay, these 2 points are close, so I'll make this as one cluster. Okay, these 2 next points are close, so I'll make this as cluster. Okay, these 2 small clusters are close, so I'll combine these 2 small clusters and make it one big cluster. Now, when it is combining these 2 smaller clusters, right, and making a bigger cluster, the hierarchy stays true that these 2 smaller clusters are subgroups within this. Okay, and this is one specific reason why hierarchical clustering is used in what is called as product classification. So how many different product lines should a company have? So the companies use this to analyze and consolidate product lines. Let's say some products are not doing well, or some products don't have too much differentiation in terms of features, right, that they have, or in terms of the revenue that they are making. They club those 2 products and instead make it a single product, or repackage that stuff, or remove one particular product entirely, right? So that way what they do is they consolidate their product lines so that they have some minimum number of product lines to manage. So think of a cereal based company, right? Now, if you think of cereal based company, there are, let's say, Kellogg's itself, right? There's Frosted Flakes, there is K-Lite, there is the regular Kellogg's cereal. There is so many different types of cereals under Kellogg's, right? And each of those cereals has a different type, like in the sense that the size of the box, right? There's a family size, there's a super size, there's a saver size, saving size, there's a small size, there's a cup size, right? So all of these kind of become a difficult thing to manage in terms of inventory, in terms of manufacturing and everything. So at sometimes what companies do is they try to consolidate these things. They try to see, hey, I am producing the cup size of K-Lite, or am I producing the cup size of Frosted Flakes, but am I really making that much money from it? Or is it similar? Like, what other cup sizes are being sold better than Frosted Flakes? So in order to do all these kinds of analysis and consolidation, one part of that analysis is a clustering like the hierarchical clustering, which kind of tells them that, hey, these are all the various products you have. These are all the similarities, or these are all the transactions that are being made. This is how you can consolidate. Let's go back to the notebook. So as I said, it's a bottom-up approach to clustering. Initially, n data points are created as n clusters, with each point in its own in a cluster of its own. Then for each cluster, the data point is compared with the nearest point. Pairs of data points which are nearest to each other are grouped together to form clusters. Then they are combined to one cluster. This process is done iteratively until clusters are grouped together one by one based on nearness criteria. This method is followed until a hierarchy or a tree of clusters is formed, and then we get back all the data merged to form a root. Then a cut is taken at any point to visualize the groups. So this is basically how it works, right? So there is something called as a dendrogram, right? So now where here it was explained, right? This method is followed until a hierarchy or a tree of clusters is formed. Okay, this is the most important piece of a hierarchical clustering, because so if you remember in k-means and dbscan when we studied, we used methods like Salute score or elbow method or AIC by BIC, right? Those kind of criteria, information criteria, criterion methods, metrics to determine what are the optimal number of clusters in a group, in a data set, right? Here in hierarchical clustering or agglomerative clustering, you don't do that. Instead, what you do is when you run the model, when you run hierarchical clustering or agglomerative clustering on a data set, it comes up with this dendrogram, right? So it does the bottom-up clustering method. So it picks each point as its own cluster in the first iteration. As iterations progress, it will check what points are near and start building clusters, right? At each iteration, clusters are kind of typically halved, right? So let's say you start with n points. The second iteration, you will have n by 2 number of clusters, right? Because every 2 points are paired up together and you get n by 2. So then n by 2 is halved n by 4. N by 4 becomes n by 8 and so on. Like that until it approaches 1 cluster, okay? So, and that's how basically it's built up. Now, this kind of an approach, right? It is visualized in the form of something called as a dendrogram. And this is what is called as a dendrogram. This is how it looks like. You guys seeing this, right?
Yeah.
So if I have to explain this, right, it starts off, let me annotate. All right, so it starts off here on the bottom, right? Okay, so you see there are so many different points. Then they start getting combined by, okay? Now, okay, 1 second. So what I want to show is really, this is a level where there is only one cluster, okay? These two basically signify that it was 2 clusters before this. Now 1, 2, 3, 4. So this was 4 at one point. The next one, 1, 2, 3, 4, 5, 6, 7, 8, right? This was 8 at one point, right? So you understand how this is being built right now, right? So each line, before it hits this particular flat line, right? Each line is a cluster, right? On the top, it is one cluster. Then you have 2 divisions, 2 vertical lines running down. So it is 2. Then you have like 4 different vertical lines at the next level. Then you have 8 and so on and so forth, right? The number of children that are there at each point. Then you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Wait, hold on. I lost count somewhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah. So that will be 16 in the next level and so on and so forth. Like that, it keeps growing, or rather that's how it is consolidated in a bottom-up approach. Now, why this dendrogram is important is it basically visualizes. So this, what you see on y-axis, right? On x-axis, there is basically no axis here. It's just number of points that are there, right? On the y-axis, it's the information criterion that's plotted. It's the nearness criterion. And what happens with that is, so hold on, sorry. Yeah, so it basically tells you the length of these things, right? And it kind of determines, it visually shows you what is the size of that cluster, right? So this is a big sized cluster, but not as big as the other one. And these are the 2 different clusters that are formed when it's in the last but one step, when the algorithm is coming to an end, right? It starts off with endpoints and starts combining points together and so on and so forth, right? At a point, it combines all your data points into 2 different clusters before making it into one super cluster, right? This is that one super cluster step, and this is the 2 cluster step. But okay, but here, right, depending upon the size of these things, you can determine that one of them is, this is the shorter length, This one represents the larger length, right? And this one is further split into all these data points. This one is further split into all these red data points. Make sense?
Mm-hmm.
So that's how these things, this clustering works. Now, what's the value of this dendrogram? Apart from this visualization aspect, it will tell you the optimal number of clusters. And the way you get that is by drawing a line, a straight line across, and trying to split at a specific point. I will explain that to you guys in the next class because I need a better visualization than this to explain that to you guys. So I will come up with something which is pretty evident. So the way you draw that figure is based on one of these heights, right? The length of this. So, and the concept goes that the longest length you can go uninterrupted, right? Traveling uninterrupted by the next horizontal flat line is the that's where you have to draw a flat line and say that this is the optimal number of clusters. Let's assume, for example, that hey, this is my longest length of uninterrupted length, right? So and then I'll say that okay, 2 is my optimal number of clusters for this particular dendrogram. But I want to show you guys a different figure because in this case, it makes you feel that, you know, in every case, 2 might be the, you know, optimal number of clusters because you'll obviously find the biggest height of these either of these two branches at the top level. That's not always true because you can have a dendrogram which looks like this, right? For all we know. Okay, so if this is how it would look like, that would mean that, hey, these two clusters, right? This is not the longest uninterrupted length, right? Even the second one is uninterrupted. At the second level, it is still uninterrupted, right? And it is longer. This part is longer than this, even though this is a bottleneck. So I just need a better visualization to show you guys because this is, although it's showing a good dendrogram, it is not kind of telling you clearly where you can make a cut and what is the optimal number of clusters. So let me in the next class show you guys what the optimal number of clusters are. But what you do is, and how you calculate them is, you cut this dendrogram using a horizontal line at a certain point, right? And how many ever number of horizontal lines it passes through, vertical lines it cuts through, that's the optimal number of clusters. Let's say if this is my line, how many vertical lines am I cutting? 1, 2, 3, and 4. So 4 will be my optimal number of clusters. Or if it will cut somewhere here, right? Let's say here, it will be 1, 2, 3, 4, 5, 6, 7, 8. So like that, that's how you decide what's the optimal number of clusters. So how do you draw that line is something that I'll explain in the next class with a better visualization. So if you see in this piece of code, right, example code, we are taking a default data set, something that we create using the makeMoons function. Then there is the spectral scipy.cluster.hierarchy. So it's in a different library. It's not in a sklearn. This clustering method is in scipy library. So from scipy, from cluster, you import hierarchy and then import dendrogram and linkage, right? So linkage is the one which basically, so see here you're setting Euclidean means Euclidean distance between 2 points. That's what's calculated. That's simply the shortest line that's connecting these 2 points, right? And then there's average. So that's another parameter that you specify. So how am I going to calculate, or how am I going to grow my clusters? I will look at the average distance between 2 points in a given cluster, and that's how I will determine if these 2 clusters are closer and should I merge them or not, right? That's the average method, and this is the data set itself, moon_df. And once I do the linkages part, the clusters themselves are created. And once I do that, I just pass the linkages piece to dendrograms and dendrogram, that function. And that function is what kind of spits out this visualization that kind of shows me. Again, here, if you see, it kind of shows me that the longest uninterrupted lines are, here, and 2 is the optimal number of clusters. So I'll come up with a better visualization next class, so we can discuss that. So let's get back in next class again. So it looks like this is using sklearn library. So the first piece of code was showing you how to implement this model from the SciPy library using dendrograms and linkage. In sklearn library, if you're using that, then you will use sklearn.cluster and import agglomerative clustering. It's the same thing. And then what you do is you basically, again, the same data set, it does a fit, and then you get clustering labels from here, and then you visualize your data set, right? Again, so here, the difference being that we were using make blobs. So these are blobs. Moons is a different function. And this is the iris data set. For the iris data set, this is the clustering application, right? And then name iris setosa. So these are labels, I think, that we are visualizing post the clustering, right? So you can basically compare what cluster labels the clustering model has generated and what clustering labels your data set itself has. And based on that, you can identify what's the difference, right? Obviously, if there is an overlap between the observations, let's say in this case, right, iris virginica and iris versicolor are overlapped. So when you perform this hierarchical clustering, it will showcase iris setosa as a different cluster, right? Because of the similarity in observations. But for virginica and versicolor, it will still fail to cluster these. Instead, what it will do, right? Because if there is overlap here, what will end up doing is it will show this as one cluster, it will show this as one cluster, it will show this as one cluster. Make sense?
Yeah, it does.
But that's a fun thing to check out, like how it's gonna turn up. And that's the exercise all about. All right. That's it for today's class, folks. We'll meet in the next class on Wednesday. We will refresh. I will go through agglomerative clustering again. I will put a online article again, reading additional reading material for this concept as well. I'd like you guys to go through them. And what I would like to also encourage you guys is go through every other older notebook as well, right? Be it, try to do that. Go through hierarchical clustering, go through k-means, go through dbScan, go through PCA. If you do have any questions, next class is the one when you can ask and we can sit and clarify those questions.